Welcome, everyone. Thank you for attending today's webinar. We have a great presentation for you today on thermocouple versus IR camera measurement. Your presenter today is Dave Purcell, FLIR's Director for the Science segment. Thank you, Dave.
Thank you very much, Jackie. Good day, everyone, and welcome. We do appreciate you taking time out of your schedules to meet with us for the next 30 to 40 minutes, discussing the key differences between thermocouples and IR cameras for temperature measurement. The agenda for today's webinar is shown as follows. First, I will share a real-life example of a company that uses both thermocouples and IR cameras for conducting temperature measurement and the experience they had using them. I will then follow up with a review on how we currently measure temperature with measurement technologies that are available today. Then I will explain the basics of how thermocouples and IR cameras work. Following this, I will conduct an experiment using thermocouples and an IR camera to measure temperature. And I will conclude the webinar by reviewing the results of this experiment. We recently received a phone call at FLIR from one of our refinery customers. And this particular customer had purchased a portable handheld infrared camera for imaging and conducting temperature measurements of their furnace tubes. The individual who was using this camera had been trained and tasked with making the tube measurements. He had discovered some measurement discrepancies between his camera and 4 permanently installed thermocouples. While these 4 permanently installed thermocouples were reading around 750 degrees Fahrenheit each, his camera was indicating 1,300 degrees Fahrenheit. And based upon the melting point of the furnace tube material, this particular thermographer went into alarm mode and warned his management that they needed to shut down the furnace before it fails. Well, unfortunately, his management believed the thermocouple readings over the camera measurements. And this led to a failure of the furnace burning down and ultimately cost this particular refinery customer $20 million. Now, eventually, the furnace was rebuilt and the refinery was started up again. During the commissioning phase of the furnace, the thermocouples indicated 750 degrees Fahrenheit. Yet his camera indicated 850 degrees Fahrenheit. Well, the thermographer decided to keep a very close eye on this system and track the progress over time. And 2 months later, the thermocouples were still reading 750 degrees Fahrenheit, but his camera at this time was reading 1,350 degrees. Well, the thermographer obviously became suspicious with the varied readings, and he decided to call us at FLIR. And we at FLIR wondered about the calibration of his camera system, so we decided to send him one of our demonstration cameras. This would allow the thermographer to perform a measurement check and validate his camera calibration. Both the plant camera and the demo camera ended up measuring the same temperature of 1,300 degrees Fahrenheit. Now, using this backup information, this thermographer was able to convince the plant to increase the flow rates through the tubes in this particular furnace. And this action averted another crisis. During the next turnaround, a closer examination of the thermocouple measurement system revealed that the thermocouples had lost their calibration. And today, the thermographer and his camera are now more credible in the eyes of the plant management. In summary, from this example, we learn at this particular refinery, the management assumed that the thermocouple measurements to be the truth, and they did not trust the IR camera results. This assumption, of course, resulted in equipment failure, equipment replacement, and unscheduled plant downtime. The assumption cost this company time, resources, and ultimately $20 million. Well, learning of the potential devastating impacts of inaccurate temperature measurement, let's briefly review what it really means to measure temperature. First of all, do you realize that there is no direct method to measure the absolute temperature? All temperature measuring devices report a temperature value by measuring an effect of temperature. For example, a thermistor actually measures changes in resistance associated with changes in temperature. A thermometer measures changes in volume associated with changes in temperature. A thermocouple measures changes in voltage associated with changes in temperature. And an infrared camera measures changes in IR radiation associated with changes in temperature. All of these instruments report a temperature value based upon the measurement of some other parameter. Now, for today's presentation, first, let's review some of the basics of thermocouples and how they work. It was Thomas Seebeck in 1821 who was credited with the discovery of the thermocouple. He discovered that a conductor is subjected, when a conductor is subjected to a thermal gradient, that the conductor will generate a voltage. This effect is known as the thermoelectric effect. Now, the science behind creating a thermocouple is actually quite simple. If we take two conductors of two different materials, in my schematic I show a metal A and metal B, and I expose them to the same heat source, we will get two different induced conductor voltages. We can measure the difference in voltage created by these conductors for various temperatures and calibrate the system. A given temperature input will produce a specific voltage output. Knowing this temperature-voltage correlation or relationship will allow us to determine a temperature value for an unknown temperature source from the measured voltage. Now, in our thermocouple circuit displayed here, you may have also noticed a third metal connected to our conductors. That is metal C, listed in our illustration. This third metal connects our conductors to our voltage meter, so we can read the voltage difference. As you may have guessed, these new connections introduce two additional junctions to our circuit or to our system. This essentially creates new thermocouples in our system. As such, it is critical to maintain these two new junctions at the same temperature, so as the intermediate metal will have no effect on the output voltage. In this case, we use what's called an ice bath to create and maintain a cold junction. Now, these ice baths can actually be electronic in controlling and knowing this temperature. In fact, an additional benefit of having the cold junction is that knowing the temperature at the junction provides a reference that will allow us to determine the actual temperature measured at the hot junction, where we're interested in measuring the temperature. Okay. In this example, we are referencing a FLIR T420 infrared camera. Now, this camera has an uncooled microbolometer, focal plane array, infrared detector. And a microbolometer is a thermal-based sensor, meaning it produces a resistance change when heated. Now, the focal plane array that we have in this camera contains 320 by 240 or over 76,000 detector elements, each one of those elements being a single bolometer. With the lens of our camera, we can focus infrared radiation onto these detector elements. And as the radiation strikes our elements, they heat up and their respective resistance changes. Utilizing a readout integrated circuit, we can measure the resistance change for each and every one of those elements and convert the reading to a digital count. Most cameras digitize at 14 bits or 2 to the 14th power. This digitized data for each of these elements is then calibrated to a temperature value. Those elements are then assigned a color or a grayscale value and presented as an image. and that is the basics behind the operation of our infrared camera. We can use analysis tools to highlight specific elements and display their respective values. For example, I can use an area tool to display the maximum, minimum, or average temperatures within an area. I could also use spot tools to display the temperature values from any of the elements within my image. It's like having up to 76,000 spot pyrometers or thermocouples available to extract temperature values. Now, in summary, the two measurement technologies that I've just been speaking of, thermocouples and IR cameras, neither of these technologies measure temperature. They measure an effect of temperature. The thermocouple, again, measures changes in voltage caused by heat. And the IR camera measures, in this particular instance, changes in resistance caused by heat. And that's because how the microbolometer detector in this camera works. Now, both of these instruments report a calculated temperature output based upon the respective unit measurements. Now, I mentioned in our agenda, conduct an experiment today. And we're going to use this experiment to compare the two measurement technologies that I've been talking about, thermocouples and infrared cameras. It's a simple experiment. I'm going to fix a thermocouple to the inside and outside of a tin can at the same location. And I'm going to fill the can with hot water. I will then take measurements with the thermocouple and the IR camera, and we'll compare the results. A little background to the camera. For the experiment as a thermocouple, I'm going to use an X-Tech thermocouple. And this is a type K thermocouple, which is a chromel-alumel thermocouple. And there are actually several types of thermocouples available, and they include E, J, N, B, R, S, T, C, and M type thermocouples. And each of these types are made up of different metal combinations, and they all have various sensitivities, measurement ranges, and costs associated with them. The type K thermocouple that I'm using in this experiment is the most common and general purpose thermocouple available today. It has relatively good sensitivity and it's relatively inexpensive. And the image that I show here is taken from the camera, and it's an image of the thermocouple attached to our can. The can is filled with hot water. What is it that we can determine from this image? Well, first of all, the image temperature scale, which is located to the right of the image, indicates our color temperature distribution, where the maximum temperature display corresponds to the lighter colors in the image, and the minimum temperature display corresponds to the darker colors. So from this understanding, from our color display, we can see that a temperature gradient has been established along our thermocouple leads. And that's how the thermocouple should work, so we apply that thermoelectric or Peltier effect. But what does this image tell us about the thermocouple reading at the surface, and are we measuring the surface temperature? Well, let me provide some additional background to our setup here. This electrical tape has an emissivity of 0.95. This tape is a great emitter of infrared radiation. Now, assuming the tape has reached temperature equilibrium with our surface, the color or temperature of the tape is a good indicator of the can surface temperature. So looking at the tape, I should be able to determine what the surface temperature is of my can. And from the image, we can see that we have a relatively uniform color throughout our tape surface, indicating we have a relatively uniform apparent temperature. Now, if the thermocouple is reading close to the surface temperature, what color should it appear? Shouldn't it be the same color as our tape? Yet what I see in our infrared image is that the thermocouple is actually reading something slightly less. So now let's look at our experiment from a visible perspective, where T1 is the outside surface measurement or thermocouple, and it is reporting a reading of 99.1 degrees Fahrenheit, and T2 is at the same point inside the can reading the inside temperature, and it's reporting 114 degrees Fahrenheit. Clearly, these readings are not the same. Why is that? What is going on or occurring that we have such a huge temperature difference between the internal and external measurements? Well, let's explore the possible causes for this inaccurate measurement or difference in measurement. Our thermocouples do not exist in an isolated environment. These thermocouples are not only subject to the effects of conduction, but they are also influenced by the effects of radiation and convection. Now, the images I've displayed here were taken with a very sensitive infrared camera, and the variation that you see in the grayscale display indicates subtle temperature variations caused by natural convection occurring at the surface of our warm can. It's from air heating and cooling on the can surface. Now, while the effects of natural convection are certainly impacting our thermocouple temperature measurement, they're really only contributing about a 1 degree variance. So this really doesn't quite explain why we are seeing a 14 degree difference from our internal to external measurements. So let's take a closer look at our experiment. Now, thermocouples are typically very small, and intuition tells us that if the mass of the surface or of our can is very large compared to the thermocouple, heat transfer will be adequate for measurement. I guess the question is it? I should note at this point that all temperature contact sensors require appropriate mounting so that they can achieve the same temperature as the surface in which they are in contact with. Now, considering the geometries of our flat and curved surface of our can and our spherical bead thermocouple, we need to ask, do we have sufficient contact for adequate heat transfer to occur? Now, my gut is telling me we do not. However, through some additional testing, I believe we should be able to confirm this. So let's do an experiment redo. Let's introduce another measurement source. Let's use a permanently mounted thermocouple. And in this example, let's use an omega type K thermocouple. Now, this is a permanent thermocouple, and it requires it to be cemented to our can surface with a high temperature, high thermal conductivity cement that requires a 9-hour cure time at high temperature. And you can see I've displayed in my thermocouple here the temperature of 213 degrees Fahrenheit. And note that anytime you use cement with a thermocouple to permanently attach that thermocouple, that cement must be very thin, it must be conductive, and present the least amount of thermal resistance possible. And we've applied our removable thermocouple again, and we filled our can with hot water. We can look at our IR image of our can. Now, the IR picture tells us that the cemented thermocouple, which is the couple on the left, is at or near the same temperature of our surface, while the temporarily fixed bead wire thermocouple clearly isn't. We see some cooling going on there. We see that this visible perspective confirms our thermal image qualitative assessment, which is the permanent inside thermocouple and the permanent outside thermocouple measurements are fairly accurate and close. In fact, they're 1 degree off only, while the removable outside thermocouple is off by more than 17 degrees. Now, the chart I'm displaying in my next slide compares the measurement results from all of our measurement instruments. In general, the cemented or permanent thermocouple and IR camera produce fairly accurate results, while the bead wire or removable thermocouple results were very unreliable. These results confirm our original assessment of the temporary mount. It confirms our gut feeling. We clearly are not making the necessary contact with our surface for adequate heat transfer to occur and for accurate temperature measurement to result. The next chart is a summary of the results from our experiment. And in closing, let's review the results of our experiment and what we have learned about thermocouples compared to infrared cameras for temperature measurement. First of all, we learned that temporary installed or bead wire thermocouples, while they're inexpensive and the most generally used thermocouple, they do not make very good surface temperature measurements. And it's very difficult to get good heat transfer between the target surface and the thermocouple. The thing with bead wire or temporarily placed thermocouples is they do make good measurements in liquids and fluids and also in gases, but they do fall short when it comes to surface measurements. Other disadvantages include that they're limited by the number of measurement points you can make, and you do require contact with the target of interest to make a measurement. Second, we learned that the permanent or cemented thermocouples give very good surface temperature measurements. However, they do require fixed mounting, making them non-transferable. Additionally, they are adhered with a cement that requires heat temperature exposure and or high temperature exposure and long cure times. Now, using this type of thermocouple could create some complexity if you are looking at a target or trying to measure a target that requires multiple point measurements. And like temporary thermocouples, you are limited by the number of measurement points that you can make. And of course, contact is required when utilizing these technologies. Now, finally, we learned from our results that the IR camera is actually fairly accurate for surface temperature measurements. The camera images as well are very easy to interpret. By just looking at the images, we could see that there was a temperature gradient along our thermocouple, but we could also see that there was a difference in the temperature of the thermocouple and the surface. Also, we learned that with the IR camera, we can extract measurement values from several thousand locations. It is, however, important to know the emissivity of your target to get accurate temperature measurements. This closes our webinar for today, comparing the results of thermocouples and IR camera for temperature measurements. For more information regarding infrared cameras or thermocouples or the content that we addressed today, I would direct you to our partners.
Well, thanks everybody for joining us today. And thanks, Dave.
You're very welcome. Thank you again, everyone.